Auxiliary cooling serves as a mission-critical availability system, protecting the essential network and control services that support the main IT load. This 3D cutaway diagram maps the physical boundary of that auxiliary infrastructure. Beyond the main data hall, peripheral spaces like the Network Operations Center, the main mechanical room, network equipment rooms, and battery support areas sit on the edge of the critical footprint. Calculating redundant thermal capacity is only part of the equation. The actual system topology must be dictated by the specific outage consequence and the allowable recovery time of each distinct room. This table categorizes consequences. Class A spaces carry immediate service risk, requiring strict 2N or N+1 topologies with independent mechanical and electrical paths. Class B operational spaces tolerate N+1 duty standby configurations, while Class C occupied areas, like offices, utilize standard VRF zoning by area. Applying mathematical capacity redundancy to these spaces is useless if the physical delivery paths eventually converge. This is why engineers conduct a failure domain review. A failure domain review identifies shared elements that act as common mode denominators. A single shared condensate drain header, one centralized gateway controller, or a solitary automatic transfer switch can instantly defeat a massive 2N architecture. True redundancy in these critical environments is only achieved when the cooling systems are physically isolated from one another and mathematically proven to survive a single point of failure. This infographic illustrates the concept of the availability chain. A support space is only as resilient as the weakest interface connecting the room's heat load to its final external heat rejection. To maintain that chain in electronic environments, we target a very specific thermodynamic metric. The sensible heat ratio, or SHR, must be tuned to 0.90 or higher. Standard comfort cooling equipment operates with a lower SHR, designed to pull moisture from the air. Placing those units in a dense electrical room wastes significant capacity and energy on unwanted latent dehumidification, instead of dropping the dry bulb temperature. Achieving these continuous sensible targets requires highly specific hardware, starting on the roof with the outdoor heat rejection equipment. This Daikin VRV unit ensures continuous operation for constant UPS loads, providing reliable cooling below -20 degrees Celsius via wind baffles and EEV head pressure control. Over its 15-year life cycle, exterior coils require epoxy phenolic coatings, passing a 1,000-hour salt spray test. Internally, large groups of inverter-driven VRF compressors pose a risk to the facility's power quality. They must utilize active front-end inverters or integrated line reactors to keep total harmonic distortion below 5%, strictly complying with the IEEE 519 standard. Looking at the indoor equipment, this rectangular ducted fan coil demonstrates why nominal kilowatt ratings are insufficient alone. Engineers must verify the unit's external static pressure capabilities and airflow distribution limits against the specific physical constraints of the ductwork and the room layout. Specifying the exact equipment limits, ranging from harmonic distortion caps to psychrometric performance, is the only reliable way to build a reliable availability chain. Selecting the right equipment is the prerequisite. Translating that into performance requires understanding the thermodynamic reality of the VRF cycle. This diagram tracks the 4-step loop. The compressor forces low-pressure vapor into high-pressure vapor. The condenser rejects heat, yielding high-pressure liquid. The EEV throttles liquid to drop pressure, and the evaporator absorbs room heat, turning refrigerant back into vapor. In the field, that perfect physical cycle is constrained by the piping route. Engineering limits cannot be copied from generic pipe tables. A proposed route only passes when the original equipment manufacturer's software explicitly verifies it. The math must account for the actual equivalent length, the vertical lift separation between units, and the exact downstream distance from the first branch joint. Executing this route requires strict installation discipline to maintain system cleanliness. Copper joints must be brazed using a dry nitrogen purge for a clean, oxidation-free seal. Once sealed, technicians perform a critical safety calculation. The exact refrigerant inventory is tabulated by combining the factory equipment charge, specific pipe segment additions, and branch component allowances, verified on-site via precise digital scales. This precise mass is required for ASHRAE 15 and 34 safety compliance. The total releasable charge must be calculated against the volume of the smallest affected occupied space to ensure leak concentrations remain below toxic or oxygen-depleting thresholds. When utilizing lower global warming potential A2L refrigerants, like R32, the mild flammability introduces code-mandated mitigations. This often requires localized concentration monitoring linked to mechanical ventilation interlocks. Without rigorous installation discipline and strict volumetric safety calculations, the underlying physics of the refrigerant cycle will eventually defeat the mechanical design. To prove the design works, facilities execute a sequential commissioning proof chain. Reliability is validated from level 1 through level 5, and tests conducted later in the sequence cannot compensate for steps missed early on. Level 3 covers startup requirements. The system must pass a nitrogen standing pressure hold, a deep vacuum micron decay test, and a precise scale-measured charging process before any compressors are energized. Level 4 shifts to functional testing. Technicians prove the sensible net capacity matches the load, verify the external static pressure holds up at a simulated dirty filter state, and validate the programmed control logic. Part of that logic involves the automated microcontroller rotation for lead and lag units. This ensures run hours are equalized across redundant systems, preventing one unit from burning out while the standby sits idle. For automated staging to execute safely, exact permissives must be met. The controller must verify healthy input power, confirm normal condensate levels, and read 0 active safety lockouts. Condensate management itself is not a plumbing afterthought. In a data center, the condensate path operates as a critical electrical safety system. If a drain line clogs, the pan fills and lifts a high-level float switch. This instantly triggers a hardwired interlock, snapping an electronic liquid line valve completely closed. This hardwired interlock must immediately cut the liquid line cooling and trigger alarms. The alternative is a catastrophic condensate overflow, raining directly onto active switchgear or server racks. Rigorous functional commissioning is the only process that translates theoretical cooling capacity into a physically proven defensive network. The final testing phase is Level 5, Integrated System Testing, or IST. Here, the facility validates the mechanical systems against simulated catastrophic edge case failures. A critical failure scenario is the transition from the utility grid to backup generator power. If all compressors attempt a simultaneous step-load restart, they will immediately crash the emergency bus. This graph plots the solution. The units require fast auto-restart capabilities paired with a staggered staging timeline. The controllers hold back the mechanical load, stepping it up incrementally only as the emergency generator frequency curve stabilizes. During these rapid emergency startups, crankcase heater sequencing is vital. Fast-acting heating loops pre-warm the oil during standby states to protect the compressor mechanics from destructive liquid slugging when the inverter spins up. Next, the commissioning team simulates a controls failure domain by severing the connection to the central BMS gateway. This proves that local autonomous logic will continue to sustain the critical cooling duty without central supervision. To simulate a power failure domain, engineers drop the primary A bus breaker. They must confirm that the independent B circuit completely picks up the thermal load without requiring human intervention. Finally, they introduce an environmental fault, such as physically blocking condenser airflow to simulate high outdoor air recirculation. They verify that the outdoor unit detects the resulting head pressure spikes and dynamically activates capacity derating logic, preserving partial cooling instead of triggering a complete hard system trip. True Tier 4 fault tolerance is defined by this behavior. It is a system's ability to execute fail-safe protocols independently, surviving severe edge cases without relying on central intervention. When these edge case failures eventually occur outside of a controlled test, facility operators must follow a rigid troubleshooting doctrine. The prime directive is absolute: stabilize the room temperature first. Technicians must never defeat or bypass physical safeties just to force a compromised compressor to run. Operators must validate actual physical sensor states using handheld meters at the equipment. Relying solely on what a centralized BMS graphical interface displays can mask localized mechanical faults. To isolate specific failure domains, Operators use an alarm priority matrix. This filters standard advisory alerts, like filter maintenance, up through medium threats, like a gateway loss, up to high-priority unit trips, and finally, critical events, like a high room temperature. The rule for system restoration is strict. Repairs are completed and manual alarms are reset, only when the physical thermal trend curve provides absolute evidence that the room has recovered. Guaranteeing zero downtime for Tier 3 and 4 support spaces depends on relentlessly mapping, testing, and physically proving the mathematical independence of every link in the availability chain.